Okay, hi everybody. Welcome to our first meetup. So what we're going to do is that for about an hour, I'm going to talk about FHE and what homomorphic encryption is. You don't have to know anything in cryptography. It's really meant to be very, very high level. And we're trying basically to abstract away all the gory details, you know, the airy math that is behind FHE so that you can get actually an intuition of how it works. And it's also a very good introduction to concrete. We'll show you how it works. And I will try to share my screen now. Can you guys see my screen?
Yes, we can.
Yeah, perfect. So I'm gonna start with a very high-level perspective on what FHE is. So we're not going to assume that you're a cryptographer. We're just assuming that you have probably a very diverse background. But what you have in common is like a few notions in cryptography, like you know what public key encryption is, like regular public key encryption. And you're probably also a developer or tech savvy, or you're interested in these kind of technologies. So first of all, what FHE is basically this holy grail of cryptography. I'm going to talk about the timeline and the different avenues of research that conducted to the discovery of homomorphic encryption. But in the meantime, FHE is this, what you have in front of you. So basically you have these basic primitives. You can encrypt a data X, resulting in a ciphertext. To do that, you're using, typically in the symmetric setting, you're using a secret key to do that. So the secret key serves both for encryption and for decryption. So it's really the symmetric setting, like for AES. But there is also a public key. And this might seem a little strange at first because we're talking about a symmetric scheme, but at the same time, there is a public key. And this public key is actually used by somebody else to basically take your ciphertext or bunch of ciphertexts and then perform some homomorphic operations on them. And resulting at the end of these homomorphic operations, resulting in a ciphertext of the result. And then this result is just sent back to the user to be decrypted, but nothing has transpired in the throughout. I mean, in the middle of the computations. So this seems a little bit magical. There is also this, I would say, asymmetric flavor of FHE, where you, instead of having using the same secret key to both encrypt and decrypt, you actually have a public key for encryption. So this is really reminiscent of regular public encryption, where anyone can actually encrypt, but you're the only one having the decryption key. And so using this kind of FHE is actually very, very useful because you can let other people than yourself providing data encrypted under your key. So instead of having just one source of encrypted data, now you can just have a lot of people contributing to the computation for you. So it's a little bit weird, but we have these two public keys. So instead of saying the public key, because there are two public keys, we're just going to say that there is a public encryption key by designating keys by the way that we use them, the operations we use them for. So basically, there is a public encryption key, and there is still this public evaluation key. And what is really amazing, and that shows that homomorphic encryption is not like regular encryption, is that actually the two settings are equivalent. Asymmetric and symmetric FHE, you can build one from the other. So I'm not going to get into the details here, but just so you know, although there is a huge difference between asymmetric encryption, like AES, for instance, and RSA or Gemalto or other public encryption schemes, here we have an equivalence between the two. So this already shows that we have something very special in terms of a cryptographic object. And what it allows you to do is basically to encrypt data both in transit and during and in processing. So it's basically for this trilogy of data at rest, data in transit, and data in use. You can basically protect the data across the entire life cycle of these data. And so this is, as an example, this is like super valuable for cloud-based services. So it's usual that you have some kind of a cloud-based service operated by some company, let's say Cloud Inc. So right now they provide value-added services by aggregating data, but of course, because there's no privacy or there's a lot of privacy threats in real life, you don't have a strong guarantee of the confidentiality of your data. But using homomorphic encryption, right from the beginning, what you're sending to this service is actually encrypted under your key. So the entire rest of the universe might be colluding against you. You're the only one with the secret key. Nobody can have access to your data in the clear. So this gives you this empowers you with a very strong sense of privacy. Confidentiality is ensured. Intrinsically, your consent is required so that data can be processed. And there is a notion of data sovereignty. So it puts the user back in the middle of the picture, instead of having data being data that you own, that is basically being manipulated. You don't know where. This time you're actually the one in control. But this is also very interesting for companies, because basically, in this case, the company is not responsible for the semantics, the content of the data, because it learns nothing about it. It has no clue about which values, all the intermediate values remain in the encrypted domain during processing. So the cloud is absolutely agnostic towards the value of the data. There can be no data breaches, because basically, as a hacker, what you would recover is basically the disk of a server containing encrypted data. So there's nothing you can do about it. And then of course, the consequence of this is that the server location is actually completely irrelevant. So that kind of unlocks, the geolocation of servers. So it might be a game changer for a lot of people in the cloud business. And if you think about it, actually, we can use FHE to reconcile privacy with the internet. Instead of having a complete jungle out there, we can just, as I said, put users back in the center, back in control of their own data, and while keeping this this coexistence of services that actually process the data. And this is kind of reminiscent of this HTTPZ vision of having some kind of a protocol, integrated protocol, that would use FHE by default, so that every time you interact with a website, you give your consent to your browser, typically to send data that you want the website to process for you. So we don't have a clue if it's attainable in the next years, but this is having an efficient FHE mechanism allows you to think forward and to make a difference in the way the internet works. So I'm going to talk about the evolution of FHE and how we came to it. So don't be afraid, it's a little bit complicated. You can see here kind of a multiply forked timeline. It started about 4 decades ago, where people in cryptography basically thought about this concept of having what they call at the time privacy homomorphism, which is basically the encryption function is some kind of a homomorphism, meaning that it preserves an operation like addition or multiplication, however they are defined. But the principle is that you perform an operation, some kind of a group law or whatever, you perform an operation on the ciphertext, and it does through the encryption envelope the same or another operation on the corresponding plaintext. And so the idea was absolutely fantastic. But of course, at the time, it was unclear if it was achievable at all. And actually, RSA, the public key encryption scheme, came about the same time, and it was the first example of a actually partially homomorphic encryption scheme because it is multiplicative. So if you multiply two ciphertexts, you get the product of the two. You get an encryption of the product of the two plaintexts. And for the next 30 years, people have been, designing schemes in a way or another that supported some kind of homomorphic operation. Myself, I work essentially on addition, but there are like plenty of examples out there in the crypto literature that show some kind of homomorphism with respect to one operation, and it's usually either addition or multiplication, modulo something or whatever. Sometimes it's XOR, like for Goldwasser-Mikali, but it's never like two operations at the same time. And there was this dream during these 3 decades of research about having a way to kind of compose the two fundamental operations, which are addition and multiplication, together, like having one scheme that supports both operations homomorphically. And it wasn't until 2009 that Gentry published this first example, which was very, very surprising at the time because people were like giving up on the idea of fully morphic encryption. A lot of people were actually questioning its very existence. So it was both an eye-opener and a very exciting new avenue of research to see this first example of a provably secure scheme that actually supports both addition and multiplication. And then we entered into a fascinating new subfield of cryptography dedicated really to fully morphic encryption. And so the GHV, the year after that came about. It's I would say, doesn't need lattices. So you can, it's an encryption mechanism that just uses integers, like modular integers or regular integers. So it's very basic arithmetics, and it allows you to understand very much, but it's totally inefficient. And unless you tweak it or you modify it in some way, it's not going to be useful. Then after that, in 2012, 2011, started to appear a bunch of new schemes. And then I would say at this point, we're culminating with these two 4th generation schemes, TFHE and CKKS. Because we can categorize basically this timeline into more or less 4 different generations, having distinct characteristics. So I'm going to explain a little bit more what these different generations are. So at the very beginning, what you have, I mean, according to Gentry's vision, what you have is a way to encrypt bits, okay? So the plaintexts are just single bits. And when you encrypt X, you encrypt Y, you can actually compute the addition of X plus Y modulo 2. So this is basically XOR. But you can also do the same thing with a multiplication modulo 2, which is basically an AND. The thing with Gentry's original idea is that the addition was pretty fast, but the multiplication was like super slow. And at the same time, it was terribly exciting because with just XOR and an AND, you have everything you need to actually do any kind of computation, because you can always represent your computation as a Boolean circuit, which you realize with these two basic operations. And so it shows, it like answered the question of the existence of FHE, which was like super new to everybody in cryptography. But then there is an aspect of FHE that was super important, which is the noise. So when you encrypt, actually, even though we write it down like enc of X, actually there is another variable in there, which is a randomness. There must be some kind of a random number in there. If there is no randomness whatsoever in the ciphertext, it means you can recover X with a dictionary attack. Just looking for, if you know what the encryption of 0 is, you're just looking for it and you'll know it's 0 everywhere where you can find it. So you need a notion of noise. And with FHE, you always have like this kind of noise budget where by just tuning the parameters, you just create this space for the noise. But the noise, as long as, if the noise remains below a certain threshold in the ciphertext, this ciphertext is correctly decryptable, meaning that the one with the secret key will be able to recover X. But if this noise exceeds the threshold, then the decryption is incorrect and you're losing the consistency of your computation. And the thing is, the more homomorphic computations you do, and the more noise there is in ciphertext. So it was a huge problem for Gentry. And so it came up with this. So one of the consequences of this is that because the noises are basically multiplied when you multiply 2 bits, when you multiply 2 random integers of the same size, basically the result, the product is as double size, right? So every time you multiply, you kind of double the size of the random. So it means as you perform your Boolean gates, the noise is going to increase like exponentially. So there must be some kind of a critical path in your Boolean circuit along which the noise is going to grow exponentially. And so Gentry had this brilliant idea of doing what is called a bootstrapping, which is using the scheme itself to kind of reset the noise or denoise a ciphertext. And so basically, if you have an encryption of X under a certain orange key with a certain noise, and you do some kind of operation on this value X, you end up with a new value Y, which has maximal noise. So it means you cannot perform any more operations on Y because you may lose consistency and it might not be decryptable anymore correctly. So what you do is basically you kind of use this other key, let's say a blue key, for which you're given the public encryption key, and you're going to encrypt your ciphertext. So it's like putting this orange box into this blue box, but now you're doing it with very little noise or even no noise, if the scheme allows. And then given the orange key, but encrypted under the blue key, if that makes sense, you're going to perform the decryption circuit homomorphically. And this is brilliant because what it does is that the orange key is going to remove this orange box. And at the end, you just have the blue box. And the blue box has a noise which is independent of the yellow noise that we had initially. And so it means that you can basically denoise ciphertext. So the problem in there was that the procedure was like excruciatingly slow. And on top of this, Gentry came up with, he had this initial vision about FHE, what FHE is, which is you do an operation, basically you're going to bootstrap because the noise is already too high. And so every time you want to do a Boolean gate, you're going to do a bootstrapping. Maybe not for the addition, but at least for the multiplication, you will have to do that. And if you do that every step, during the Boolean circuit, then it means that the size of your noise is going to remain constant because every time it doubles, you just put it back into its nominal size. So you can go on forever and just, perform computations ad infinitum. But at the same time, there was also another idea, which is, okay, if the bootstrapping is so slow, why not just getting rid of the bootstrapping? And we're not going to use it. We're just going to allocate a noise budget that is big enough to accommodate with the specific Boolean circuit that we're interested in. So we just leave the noise as it is. We're never bootstrapping. The noise is going to grow exponentially in the worst case, but it doesn't matter because at the point when you reach the output of the circuit, the noise is right at the threshold. So you cannot do one more step anymore. The only thing you can do is send that back to the user for decryption, but it's okay because you made it with the circuit that you wanted. And of course, you can always mix the two, like bootstrap when you absolutely need it. After that appeared like the second generation of schemes. So it was a definite improvement over this exponentially growing noise. So in level schemes, you can assign levels to the different noise sizes. And basically when you perform an addition, modulo 2 here, so basically if you had a level I and a level J ciphertext, you would get a ciphertext of level, the max of I and J. So, and when you do the multiplication, it's the same thing, except that it's incremented by 1. And so it means if you go through multiplications, the level is just going to be incremented every time. And when you reach a maximal level, well, if you exceed that maximal level, then you get an incorrect decryption. But there is still this notion of bootstrapping. You can, if you're desperate, you want to continue with your computations, you can always apply bootstrapping, which has the good taste of taking a ciphertext that is maximally noisy and put it back into the first level, or maybe not the first, maybe the second, or at least at some point between 1 and the maximal level L, where you can go on with your computations. So it was a definite improvement, and it allowed people like to basically have the noise growing linearly within the circuit with multiplications. So the notion of complexity, like the multiplicative depth of the circuit still matters, but it's less desperate. Like the noise doesn't grow exponentially, just linearly. And at the same time, second generation scheme, introduce like the notion of packing batching, meaning you can actually have multiple plaintext slots and execute the same Boolean circuit in parallel over all these slots at once. So it was, there again, a definite improvement. And also another one was just, instead of having to manipulate bits, you can actually manipulate modular integers, modulo something bigger than 2, like 5, or even not even necessarily a prime number, but something bigger. So this allows for computations over with bigger moduli. Then the third generation happened, GSW in 2013. It was essentially, I would say, conceptual simplification, also another way to another way to design a scheme that supports both multiplication and addition using matrices and eigenvalues and eigenvectors. But essentially, it's very slow. And so it was never going to give something efficient, something that we need, to change the internet with. But it was interesting to see that 1 year later, there was another GSW-like scheme called FHE that appeared that improved bootstrapping immensely. And then to do like one Boolean gate, it would cost like 1 second of computation, which was, day and night compared to Gentry's initial bootstrapping, which would take like 30 minutes to just compute the multiplication of 2 bits. So it was a definite improvement. And then what we're using in concrete is basically our variant of TFHE. So TFHE is this 4th generation scheme, which people associate to the GSW branch on the timeline. And in its very basic form, TFHE, so it means Torus FHE. We're using the Torus, which is basically real numbers modulo 1. So basically reals between 0 and 1. And in its basic form, you can encrypt bits. And then you have all this, all this bunch of Boolean gates, plus the mux gate, if gate, the ternary operator that you have in C. And every operation is basically bootstrapped. But at the same time, the bootstrapping is like super fast. It's like a few tens of milliseconds. At the same time, we can guarantee the security of the scheme. It arises from learning with errors, or ring learning with errors. So you'll see, if you're interested in FHE and you look at the literature, most of the schemes are actually relying on this complexity assumption. And the security of LWE is well understood now. Still a work in progress, but we can definitely guarantee a certain level of security. So now let's be concrete. So if you're a developer and you don't know nothing about cryptography, or you don't want to have to deal with the gory details of how FHE works, because there are plenty of these gory details, let me tell you, you may look at the libraries that are available out there. And you will find a number of libraries that are open source. So we're quoting a few of them here. Probably the most famous ones are HElib, which originates from researchers at IBM, Microsoft Seal as well. A few others like GNU-FHE, for instance, is actually implemented on a GPU. Latigo, which is implemented in Go, and so on and so forth. But if you look at them and you try to use them, you will see that you have like various degrees of usability and readiness. You will not necessarily be able to do something else than just experimental code. At the same time, some of them support single-threaded CPUs or multiple threads or GPUs, and each of these libraries actually has a selection of its own schemes and its own API. And there is this initiative, homomorphicencryption.org, if you're interested, that tries to put together like a common API for all these libraries, so that we have some kind of interoperability in representing homomorphic code in a sense. So we refer to this initiative for specification of a first API. But for the time being, each library is like a mess on its own. You have to, depending on which schemes it implements, it can be very complicated to familiarize yourself with the library. So what we're introducing today is basically a new library, which is called Concrete, which was meant in the spirit of simplifying everything and having people using Concrete who do not have to really care about all these gory details that I was talking about. So it's made with love for all of you who are like basically tech savvy, but not necessarily cryptographic experts. It is written in Rust so that it's fast, it's reliable, and the library is meant to be production ready. But at the same time, it features a Python wrapper to make it like simple and playful to use, and it implements Zama's variant of TFHE. And at the same time, you can have this fantastic operation, which is the programmable bootstrapping that I'm going to talk about later. So we're very excited actually to see what people are going to do with Concrete. And we hope that it's going to be a seamless experience for developers to try to develop their own use cases and everything with Concrete. So more about the different objects. So we didn't want to put out equations and big maths in there, but to give you an intuition of how Concrete works. So we have two types of encryption. So basically we have the blue type and the orange type. So the blue type is what we call learning with error, or LWE encryption. So basically what you can encrypt, it can be a single bit. It can be a modular integer, an integer modulo something of your choosing, or it can also be a real in some prescribed interval. You can also put a real value in there. And we have this other kind of encryption format where instead of encrypting one value X, you actually encrypt a polynomial whose coefficients are basically different values of X. So by polynomial, by using a polynomial, we can actually pack a bunch of x's together inside the same ciphertext. So it's very interesting because it's a notion of packing. Today, I'm not going to talk about ring LW encryption because it's more advanced, even though Concrete already supports actually operations on this. I'm going to focus on the first one, and in the next meetup, where we can update you with what you can do with ring LWE ciphertext. So the experience that you have as a developer is that if you're given an LWE ciphertext, this blue ciphertext containing your value X, so encrypted under a certain secret key and with a certain level of noise, you can look at it as just a 32-bit or a 64-bit integer, right? So this is like very familiar to all of you, I guess, that the X that is inside is actually just a machine word, like just an integer. And so you can use this format to encode, as I said, a bit or an integer or a real value using some kind of an affine encoding. But the important notion here is that there is noise on the right, on the least significant bits. And so the problem with this noise is that as you're going to do operations on your ciphertext, the noise is going to accumulate. And it's going to, because of the carry bits, it's going to propagate carry bits, random carry bits, further down the left side. So the noise grows that way. And if you want at some point to denoise the content of your ciphertext, you would have to resort to bootstrapping, which is this operation that, again, denoises and like kind of resets the level of noise. A very important distinction as well is that the computations that you're doing can be exact in the sense that there is never any approximation made. Your computation is absolutely correct like all the time, or it can be approximate. And this makes sense when you think of numeric computations over real values, because very often you don't actually need to be perfectly exact. You can accommodate with some kind of a error margin, like 10 to the -3 or something, or you can accommodate with some level of approximation. But with Concrete, you can actually choose. It just depends on the parameters that you're going to use. So you can pick one way or the other. When you take two ciphertexts, so as I said, they're homomorphic. So when you add two ciphertexts, the result of this is basically that the two 32-bit or 64-bit plaintext that are noisy and contained in them are going to be added like a regular, 32-bit or 64-bit addition. And so, but when you do that, always remember that there is this noise on the least significant bits. And when you do that, the two noises are going to be added, resulting in possibly in a carry bit. So you might lose, the least significant bit of the sum of X and Y. So you have to think about that and actually figure out which parameters you want to use so that you accommodate with the level of error that you can allow. The other operation that you can do easily is a multiplication with an integer, possibly signed integer, and the same thing happens in this context. Basically, the plain text is going to be multiplied like it was a regular 32 or 64-bit multiplication with an integer. But another interesting operation that we have is the key switch. So if you have an encryption of X under a certain key SK1, you can actually apply a key switch operation resulting in another ciphertext. So both of them are LWE ciphertexts, but the outgoing ciphertext is actually encrypted under a different key. And you need to be able to do that. You need to provide some kind of a proxy re-encryption key, which in this case is a part of the public evaluation key. We call that the key switching key that is totally public and allows you to convert the ciphertext under SK1 into a ciphertext of the same thing under SK2. The problem with that is that you increase the level of noise by doing this. It's not a bootstrapping, it's another operation, just changing the value of the secret key, but it's a very useful operation. And then you have this bootstrapping I was talking about, which in the case of concrete works the same way as basically the key switch. So you have a value of X, and you're going to bootstrap it to reduce the level of noise, and it's going to switch also the key. But the nice thing with the bootstrapping is that we can make it programmable in the sense that at the same time that we're bootstrapping and resetting the noise, we can actually, at the same time and virtually for free, we can apply a univariate function to the plaintext. And this function doesn't have to be linear or anything. It can be like any function. And so it's very interesting in that sense because it allows you to basically do nonlinear operations virtually for free. And because you're switching from one key to another key, you can always apply key switch so that you can get back to the first key again, if you want to keep the consistency of what you're doing. And key switching is actually much faster than a bootstrapping. But again, we're talking about milliseconds versus a few tens of milliseconds. So not a big deal. Programmable bootstrapping actually works by taking the function that you want to program into the PBS, programmable bootstrapping, tabulating it. And the PBS, what it does actually is some kind of a homomorphic table lookup. So you can put in there your table of values, you can sample your function, and basically you have this parameter like capital N, which you can choose, which gives you the number of the size of this lookup table. And but it's really some kind of a table lookup, and you can adjust the precision that you need using this capital N parameter. So all the PBS, what it does is that text X, it identifies some kind of an index between 0 and capital N minus 1. So it's a kind of a rounding, scaled rounding function, whatever. And it returns an encryption of the resulting entry in the table. So again, you have a different key, but you can resort to key switch to correct this. And so it's really a homomorphic table lookup. And if you want to think about what the other libraries do when they have nonlinear computations, they approximate them by polynomials, and usually of very moderate degree. Here, because basically capital N would be like 1024, it's 2 orders of magnitude or 3 orders of magnitude higher. So it's equivalent to have like a polynomial approximation, but with a huge degree. So it means you're really applying a function there. It's not just a small degree polynomial approximation, which makes PBS really interesting in practice. And to show you how it's powerful, basically you can, so if you take TFHE by itself, either you can use it to encrypt bits, in which case you can have like homomorphic Boolean gates to manipulate these bits. Otherwise, if you extend that to small integers, you will have addition, but you won't have multiplication. The scheme does not support native multiplication. But using programmable bootstrapping, you can actually emulate this multiplication. And the way it works is actually pretty trivial. If you look at this equation, which is the product of X and Y, is basically a difference of the squared sum and difference of X and Y. And so you can just take the encryption of X, encryption of Y, add them, subtract them, and program the function square over 4. And you do that on this, both on the sum and the difference, and you result basically in, again, an approximation, but up to a level of precision that you control of X times Y. So this shows you that PBS is actually a very computationally efficient way of computing things. The same way you can actually emulate division. Division is a nightmare. If you've been using the other libraries, you've probably seen that they do not support division. It's actually very complicated to do that homomorphically. Using PBS, it's actually trivial because basically what you do is that you take the encryption of Y, you bootstrap it by programming the inverse function, and then you resort to the multiplication trick that I showed just before, resulting in an encryption of X over Y. So you can do other things. You can do basically the Euclidean distance, or basically if you take X and Y, you see that as a point. You can compute the Euclidean distance of this point to the origin by just programming the square function twice, adding these resulting ciphertexts, and then programming the square root function. And this gives you, like in a few milliseconds, this gives you this Euclidean distance, this L2 norm that you wanted. You can also use programmable bootstrapping to do a max between X and Y. Again, doing the max homomorphically is kind of a nightmare. So a lot of the other libraries, depending on the use case, they actually resort to tricks to try to do this. There's always something that you can do, which is resorting to encryptions of bits. But here we don't have to do that, because the max of X and Y, if you think about it, and you can see that this equation is actually always true, is the max of 0 and X minus Y plus Y. And this function here is univariate. So you can program it with the PBS. So you just take X and Y, subtract them, apply a PBS by programming the function max of 0 and the input, and you add that with the encryption of Y. And this gives you an encryption of max of X and Y. So it's really interesting because it gives you, so there are plenty of ways out there you can actually use to decompose a multivariate function. In the very general case, you have a multivariate function, and this is the operation that you want to do homomorphically. And there are known ways to basically decompose them into additions or linear combinations and univariate functions. So if you use this trick, we have this new computational paradigm that arises from the use of the PBS, which is you just decompose your multivariate functions into a network of univariate functions and linear combinations. If you know how to do this, it's going to be super efficient, because you're going to use programmable bootstrapping to do homomorphically all these univariate functions, and the linear combinations come like for free. Every fully homomorphic encryption scheme likes linear combinations. It's never an issue. So now I'm going to talk a little bit about applications to machine learning to finish this presentation. So, so for those of you, I suppose a lot of you actually are familiar with neural networks. A neural network is just this artificial entity that takes a vector of values, a vector of weights, and what we call a bias. It does this linear or affine combination, and then applies an activation function, which is meant to be nonlinear, to this multisum. And then you output this. And so a neural network is nothing more than a combination of neurons plus other kind of ingredients. There are operations that do not include neuron, but the fundamental processing unit of a neural network is this. And activation functions, so there are multiple choices, they basically look a little bit like this. And they're always very complicated to do homomorphically because precisely they are not linear. So the way it used to be done in 2016, the CryptoNext paper was published, which was this idea of replacing this. Basically what they were using is second generation schemes, where, as I told you before, whose complexity depends on the multiplicative depth of the circuit. So what they wanted to do is to minimize the number of multiplications. So what they did is that they replaced the activation function with a square function. Obviously, you can do better with a small degree polynomial approximation. But this results in the fact that the approach is not scalable. You cannot have like apply this to deep neural networks because there would be too many, the depth would be too much, and so the parameters explode and so on. But here, a very elegant solution is to use a programmable bootstrapping instead to program your nonlinear activation function. So basically, we apply that to neural networks, and we have a first number of benchmarks. Somebody is writing on my screen. Okay. So we have preliminary benchmarks that we've recently put together, that we applied PBS to a neural network with 20 layers. So what I mean by layers is the number of activation layers. Basically for the NIST use case. So this is like the accuracy of the original network processed in the clear. It took like even less than a millisecond over a CPU or AWS. And we converted that into its homomorphic equivalent, resulting in close enough accuracies. There is a bit of a loss here, and with different parameters. And so the two first lines are for a 80-bit security, the last line for 128 bits of security. But this shows you that in a few seconds, you can actually easily perform the homomorphic inference of a neural network with 20 layers, and without a drastic change in the accuracy. So again, these results will be improved over time. These are our, I would say, our first benchmarks, but we'll still have things to do to improve the parameterization of this of the homomorphic equivalent of these neural nets. We also applied that to a neural network with 50 layers, and same thing here. With close enough accuracy, we can actually have an inference that works within 10 seconds or within 37 seconds or 3 seconds, depending on the level, on the parameters and the level of security. Not only did we that, but we also applied that to a network with 100 layers. And you see here these preliminary results. So for so the parameters here, depending on the set of parameters, you can see a huge difference in the accuracy loss here. So we're still working on this, but just to announce that we can actually go as deep as we want, because every activation is using a PBS, so we can do the activation function, reset the noise, and go on forever. And I guess this is my last slide. So what we're building at Zama is actually these 3 different layers. First, a crypto library that anybody can use, not only for machine learning, but in particular for machine learning. But the library concrete is actually agnostic towards the way it is used. It is meant to be production ready again, and to be easy to use and an instrument. But the next thing we're going to talk about in other meetups down the line are a compiler that basically takes a neural network and does everything that has to do with the conversion to a homomorphic equivalent, finding out the best parameters and so on, will be fully automatized. So stay tuned for more. In a few months, we're going to release the first version of this compiler. And of course, the compiler is meant to run in sync with the library through some kind of a runtime engine, a runtime environment. So there is an open source version of this runtime environment that also going to be released. And then our vision is to provide some kind of an inference to service where basically people can just upload pre-trained neural networks, click on the button, have them neural network compiled, deployed in the cloud, and an API is exposed that allows their customers to make inference requests to the network. So I think that's that's it pretty much. Probably took a little bit more time than I thought.
No, it's perfect. It's 5 to 7. So
okay.
we're
Cool.
perfectly in time.
Okay.
So thanks, Pascal, for the presentation. Maybe we can start a little Q&A session before the presentation of Damien.
Sure.
So we tried, there were many questions in the chat. We tried to answer to everyone by message, but it was tough. So I might have missed some questions. I propose, guys, everybody that wants to ask a question to write a question right now in the chat, so I'm sure I'm not missing everything, and I will eventually ask you to unmute yourself and ask the question to Pascal.
Oh, I'm looking at the chat. There are like a lot of questions.
A lot of questions, yes.
Okay. Okay.
Oh, okay. So there is a question by Timothy Blomberg. Timothy, would you like to unmute yourself and ask the question to Pascal?
Hello, can you hear me?
Yes, we can.
Hi.
Yeah. So Pascal, firstly, wanted to thank you. I've spent a lot of time reading your paper about the first crypto system. So the Paillier crypto system.
Yeah.
And implementing it.
That
so
was,
it's
oh, cool. Cool. That was more than 20 years ago.
Yeah, so I just wanted some more like information about what the compiler is going to be. Do you have any hints or what kind of language you'll write in, how that will work?
Yes, of course. We've been working on it for a few months now. So it's written in Python. It's meant to be open source. What we want to create is actually some kind of a community around FHE of tech-savvy developers who might not be crypto experts, but want to contribute in making FHE a reality. And so compiling, we think, is the next big challenge. It's the next big roadblock on the road, because finding the optimal parameters for FHE is currently a nightmare, and for all the schemes out there. And you cannot easily deploy and generate homomorphic programs unless you have some form of a compiler. So the compiler is written in Python. It is specialized for neural networks very specifically. So it takes as input a neural network in the ONNX format, which is meant to be kind of universal. And its output is basically a homomorphic representation of the converted network. But all the technical details about the FHE parameters being optimized and everything are taken care of. And so you don't have to do that. But of course, it's going to be open source so that everybody can contribute to actually improving the technology. And we think it's going to be, FHE is entering this new era, or it's still going to be about the crypto, but not only about the crypto. And it's going to be about software tools and compiling and programming language and making FHE very simple to use, very simple to instrument, and very playful. And yeah, does that
wonderful
answer?
Yeah, thank you very much. I'm excited for that new future.
If I can,
we are too.
Yeah.
Yes, Ron.
So, Tim, to give you a sense, FHE today is kind of like where deep learning was in 2009, 2010. It's working, but nothing exists. No tooling, no implementation that is easy to use. There is no TensorFlow framework. So we got to build everything. And this is really the way we think about this at Zama, is we want to build all the different layers so that anybody who wants to put it in production can do it without necessarily having to spend months learning about homomorphic encryption.
Exactly.
And it's a really big challenge. I mean, today we're only talking about cryptography, but really this layer, this AI framework layer on top of it is extremely complicated. And it's also something we're pretty excited about open sourcing down the line.
Mm-hmm.
Okay, we have other questions. I'm trying to look at them in the order. So we have a question from Louis Oank. Louis, can you unmute yourself? Sorry for the pronunciation of the name.
Yeah, sure. Thank you. So I see in the slides that you have here that CPU is highlighted, but I'm just wondering if you have plans to implement in GPU and FPGA.
Sure, definitely. So what we want to do is, so implementing on CPU is necessary, of course, but we need to improve efficiency as much as we can. So we have at some point to move to hardware. And the first step of this is going to GPUs, and then going to FPGAs, designing our own architecture for efficient FHE, and then possibly to ASIC. So it's going to take some more, investment and probably a lot of time and efforts, but we need to go there in terms of getting. I mean, we want to get this speed up factor that only hardware can provide. And even though the crypto is always a way to, improve the performances, ultimately you need also to improve the engineering side of things and to improve, the operations themselves, all the implementation tricks, all these engineering things that you have to do to make things fast. We also need to explore them. And so, yes, we want to go there, and we'll see. It's probably going to take years, but this is what we want to do.
Thank you.
Okay, continue with a few more questions. So we have a question from Alexander Viant. Alexander, can you unmute yourself?
Sure. So my question is about packing and programmable bootstrapping. Are they mutually exclusive, or could you combine them?
So there is no possible bootstrapping for packed ciphertexts. But what you can do basically so I talked about this blue encryption and this orange encryption, which I haven't described or anything. It's for the next meetup probably. But you can actually take blue encryptions, LWE ciphertext, and pack them into a ring LWE ciphertext. And you can also unpack them, right? The thing is, to apply the programmable bootstrapping, you can only apply it on a LWE ciphertext, a blue ciphertext. So you may use a ring LWE ciphertext to, to make things more compact, basically to compress encryptions into a single one. But basically, as soon as you want to apply bootstrappings, you would have to unpack the values in the polynomial that are of interest for you, to unpack them and apply bootstrapping on them and possibly put the results back. But so programmable bootstrapping and packing are not compatible with one another.
Great.
I don't know if you still have time or
maybe another 1 or 2 questions, then we move to the talk by Damien.
Okay.
I see a question from Guillaume. Guillaume, can you please unmute yourself?
Yes. So yeah, I was wondering, this inference as a service, who do you think is going to pay for it? I mean, do you have a real use case, some customers so who is going to pay and for what? In fact, that's my question.
Maybe around, yes.
So I mean, the short answer is when you look at other people who are trying to sell homomorphic encryption, they all seem to go after banks, governments, healthcare companies. And these industries are very good at paying for expensive POCs, but they're really not that good at putting things in production quickly. So the short answer is we don't know, and we're definitely not focusing on monetizing right now. Our goal is first and foremost to build a product that is easy to integrate. In fact, we actually have a 0 POC policy internally in the company, because what we build in open source should be so easy to use that you should never need us to do a POC. So, I don't have a clear answer to you. My answer is let's talk about it in a year. And by then, hopefully, the thing will have matured enough that we will see use cases emerge bottom up, even maybe from the community. We'll see.
Thank you.
Great. Maybe a general information. Rand already said it in the chat. The slides and the video will be shared in the channel. So don't worry, even if you were late or you missed a part, you're gonna be able to see the slides and the presentation. I may propose to stop here for the people that were not able to ask a question or for which we did not have time. Don't worry, there's going to be a Q&A session at 8 p.m. in 1 hour after the Damien's presentation. So we will give you the chance, everyone, to ask the questions you want. So don't worry if we didn't allow you to ask the question right now. So maybe again, thanks Pascal for the presentation, and we can maybe move to the presentation by Damien.
Great.
Yeah.